So previously, we had defined light, waves. So we have a wave moving to the right. We can have a wave moving to the left. It's electric and magnetic fields. And so what we've got is we've got a changing electric field. We know from Faraday's law that a changing electric field, or rather, we know from Ampere's law that a changing electric field creates a changing magnetic field perpendicular to that. So we have a changing electric field. It goes back and forth, back and forth. Okay, so it goes one way, then the other way. So that means a magnetic field goes back and forth, back and forth. But a changing magnetic field by Faraday's law creates a changing electric field perpendicular to that. And so that means each of these fields, electric fields and magnetic fields, create another field next to it that's perpendicular. And so light propagates in that fashion. And so our previous discussion of Maxwell's equations gave us the equation of light. So now we want to talk a little bit more about light and light properties because now we have a wave. We talked a little bit about waves in Physics 1. We know the speed of the wave is wavelength times frequency. So we know that property. We know that intensity is power over area. So it's another property that we know about waves from Physics 1. We talk about sound waves. So power is related to energy. So we know that power is rate of change of energy. Well, to find the energy, we need to find the energy densities. So the energy, the total energy, is going to be energy density times volume. So we have a region of space here, okay, and we can imagine it has a cross-sectional area and some x, so volume equals area times x. So we need energy density. Well, we know the energy density of the electric field. Energy density of the electric field is 1/2 epsilon naught E squared. Energy density of the magnetic field is 1/2 epsilon naught, or sorry, it's 1/2 mu naught B squared. So the total energy density will be 1/2 epsilon naught E squared plus 1/2 mu naught B squared. Well, we also know from prior to this, from our previous lectures, we also know that B, okay, is equal to E over C, okay. And so the energy here would be 1/2 epsilon naught E squared plus 1 over, or rather I guess but this is E squared over 2 mu naught C squared. Well, we also know from our discussion of Maxwell's equations that C equals 1 over square root mu naught epsilon naught. So C squared would be C squared would be mu naught epsilon naught. Okay, so the mu naughts cancel, and what we find is 1/2 epsilon naught E squared plus 1/2 epsilon naught E squared is just simply epsilon naught E squared. So that's the energy density here. And so now we have an expression for energy density, and we say, okay, so we plug that in for total energy. Total energy would be energy density 1/2 epsilon naught E squared times volume, which would be X times A. So that's the total energy. So the rate of change of that is power. So power is rate of change of that. So if we look at that, we say, well, the energy density here, and again, this would actually be probably E naught right here, the maximum energy, okay, because energy is going back and forth between the two. So this is the total energy. So that's going to be equal to 1/2 epsilon, the derivative of this. Okay, so that's power. Everything here is constant. A, so it'll be dx dt. What's dx dt? Well, dx dt is how fast this is moving, so that's the speed of light. So this becomes 1/2 times epsilon naught. Sorry, there's no 1/2 in there anymore. So it'll be epsilon naught e squared times the speed of light times a. Okay, well, that's the power. Well, we also know that power and intensity are related. Intensity is power over area. So if I want intensity, that's just going to be C times epsilon naught E squared, or E naught squared. Okay, but E naught is also related to B. So E naught over C equals B naught. So I could then rewrite this as C or rather, I could rewrite this as sorry, I had that wrong right there. So E naught equals C B naught. Sorry about that. So this would be equal to C squared epsilon naught E naught B naught. Well, C squared is 1 over mu naught epsilon naught. So it's epsilon naught. Okay, so that means the intensity would be equal to 1 over mu naught E naught B naught. Okay, now E naught and B naught are perpendicular to each other. So you can imagine that the propagation is perpendicular to both of those. Well, the thing that's perpendicular to two other vectors that are perpendicular is the cross product. So we could have E naught cross B naught, and that's going to be perpendicular, so that would be a vector in the direction of propagation. Well, it could be either E naught cross B naught or B naught cross E naught. Turns out that if you use the right-hand rule, E naught cross B naught gives you the direction of propagation. So we can define a vector that propagates in the direction of the light, and the magnitude of that vector is the intensity vector. So this is named after John Henry Poynting. So we have 1 over mu naught E naught cross B naught. Okay, and we call that the Poynting vector. When I was a student, I used to think of it as Poynting, Pointing. It points in the direction the light's traveling. It's really Poynting vector, named after the guy that discovered it, John Poynting, and so it's Poynting. You want to use I vector for that because that confuses with current. We don't want to use P vector because we use P for power and P for momentum. So S is what's normally used. So that is the Poynting vector right there. So the Poynting vector gives you the intensity. So the magnitude of the Poynting vector, that gives you the intensity. And so S is sometimes used for intensity with light. That's going to be 1 over mu naught E naught B naught. Okay. Now that's the intensity of a particular moment in time. Remember, the light actually is moving along here, and so what we're interested in is not the intensity of the waves at one particular instant, but the average intensity here. So to get the average intensity, so S average, we would want RMS values. Well, we know that the RMS value, we can get the RMS value from E naught, okay, by a factor of square root of 2. And so so if we want to have the values here in terms of the RMS values, then we need to have square root of 2's in there. Okay, and so really these should be probably RMS's. RMS are up here, and so the RMS is the naught divided by the square root of 2. So this is the average right there, and so that's going to be equal to 1 over 2 mu naught E naught B naught. Okay, so again, I made a mistake up here. These should be RMS values. Okay, So this gives us the Poynting vector right here. And so the Poynting vector it gives us a measure here of the power that's being power per area. Power per area is going to be the intensity. And so again, you can read more in the book about this, but this gives you an idea about how the Poynting vector works. So next, we can start doing a few examples of this. One thing to remember is that we do know that B naught and E naught are related to each other, so we can rewrite this thing in multiple different ways. We can say that the intensity, which is the magnitude here. So the intensity, that's the magnitude of the Poynting vector. So the intensity, or sometimes we just use S for that, can be the E RMS, B RMS over mu naught. Okay. It could be E naught, B naught over 2 mu naught. Okay. It could be E RMS, B RMS over mu naught C, or E naught, B naught over 2 mu naught C, or it could be, oh, I'm sorry, this would be E RMS squared or E naught squared because B E naught or E over C equals B, okay? Or we could say this is equal to C times B RMS squared over mu naught, or it could be equal to C B naught squared over 2 mu naught. So all of those quantities give the intensity, which is the average power. So that's the average. This is all the average value of the Poynting vector. So all those things give us the same quantity. And so now we can actually figure out from light intensity the strength of the electric field and the magnetic field. And so we are now able to start doing example problems.